Just get a survey on the audience. Who is here working on product development? One? That's it, okay. So the big question, like, the reason I'm asking this is that a lot of talks I've attended today is like in-house, pretty much people taking care of their own data in their own house. It's a difference between when you try to sell a data product to another company. You need to understand their processes, you need to understand their compliance, corporate politics, etc. So this talk is really like helping two groups. Group number one, people who want to open the door and bring their small players in to ramp up their, taking advantage of the AI or data analytics, and it's people who are struggling to get in. It's just a collection of observation that already exists in automotive and manufacturing, because I guess they're less regulated, so they have some of the best practices. But the problem there is the margin is a sort of razor thin. So kind of like it's quite a different environment to survive. Second to that is it's mostly B2B, and sometimes B2B2B2B is like chains of parts that goes into your car, like 30,000, 300,000 parts in your car. So this is really based on that. It's like ecosystem instead of an ecosystem. Like ecosystems are the one that like I only care about what I have full control of. Co-pilots here loosely is being used at augmenting the expertise of the people we already have, and then the whole talk is about the sort of last 4 years that we work with best vendors in manufacturing, and Stanley Black & Decker I'm working with. We tried a lot of products, we tried a lot of proof of concepts. Some of them worked, some of them didn't work. I ended up leading a team that is only focused on building products for our customers and their customers. Nothing in-house, like nothing looking internal. A little bit about me, my background is electrical engineering, control system, machine learning, bachelor, master. Then somehow control ended up going to mechanical department. It happens. And over there I did a stochastic optimization. And in that I looked into like the incentive, the maintenance team, into the reliability of the system. So it became about game theory. And then I coined the term contract engineering. It became a field. These are the books, except the green one that I contributed to. It's mostly about just risk-based decision-making for health of the system. Very aligned with the previous call you heard. I won various grants from NSF, DOE, NASA, etc., all in the same space. System health, from the batteries and the water of the state space, the state station, to nuclear waste canisters that are sitting in parking lots with no sensor on them. Did a few startups in some fun topics as well. My domain is all about like, so if I have a laser in here, is when the system is going bad, like it's good for a long time, then all of a sudden it ends up in these ramps. Sometimes it's a flitch, it goes bad, but everything is normal again. And then sometimes you don't have any observation, and then these are different regimens of the data. So these are the three processes I studied heavily into the data. Another thing, it's funny because it's an AI conference, we should all kind of like know what AI is by now, but I just want to put the terminology in place. I'm a follower of Michael Jordan, so like the way I see it is that AI is like an extension of a control system, which has a feedback element, you get the signal, whereas the neural net in this mechanism that you see doesn't really have feedback loop. Backpropagation is not a feedback loop, but I don't go that far. Secondary item to that is that this control system goes here. Now your reference of the model or system keeps changing. So you need another controller for your controller, which makes it adaptive control. And this is himself talking loudly, etc. You can read his stuff, are really, really good. But overall, these are the range of AI implementations we have done. And this is really simple terms. Apologies, you are already very familiar with that, but just some examples for those of you who are not familiar with automotive production. So there are AIs that do your mundane job very consistently. For example, there's a big piece of door, you want to keep moving. Obviously, you use computer vision, you look at the measurements of the piece of a rivet, thread, etc. Category 2 is that they do that job, but also they do it much faster. So the welding, like people cannot weld as quickly as robots, have you seen in many videos, riveting, etc. I don't know if you know that right now there are factories that are working 24/7. It's more than like hundreds around the world. They make 80 cars an hour. Like 80 cars comes out every 1 hour. So by the end of this call, it's 20 minutes, there are like 80 cars coming out of somewhere. It's math, right? I don't know, but so the opportunity to catch trends and anomalies is basically something that you can do really fast and people cannot do fast. So that's category 2. Category 3 is like complex task. You have diagnosticians or people who do forecasting. They spend days or months to do that. You can do that very fast. Category 4 is that we do complex stuff tasks, which is mostly cognitive detection, signal processing. These are the things that are quite invisible to human eye. We don't run wavelet to understand like a little bit of a change in a signal. Category 5 are the things that are like collaborating with the human operator. And this is not just, hey, I'll provide you data, you decide. It should be an interaction. That's my definition of collaboration. So it goes into planning, auto scheduling, and robotic process automation. Category 6 is where it hits adaptive control, which is the AI to train and adapt other AIs to adjust to the environment. Obviously, the whole promise of this call is that if you want to get there, you need to have an open ecosystem, and we get to that. So this is why we take away of this call. So we want adaptive and supervision, like self-supervision learning. Now, the other point here is that despite all of these AI in place, this is the rate of quality in the automotive manufacturing globally. It only is getting more recalls, more issues with higher intensity. So overall, you know, the best technologies are in place, best robotics are in place last many years, but the trend is not promising, and the overhead costs and et cetera. So the pillars of the solution to get to that paradigm in manufacturing automotive is, this is pretty much like you need the adaptive process control. A lot of people mix it with the statistical process control. Yeah, please read. But overall, without automatic feedback that basically runs those category 5, 6 analytics super fast and feeding it back into the controller system, you don't actually have adaptive control. You're just having people running from the Excel sheets to the system, and it creates a massive overhead. So this is number one. And then the statistic process control is just this segment of it, that you measure the small little performance of it. Number 2 is why IoT enablement is a foundational step. Without IoT, you don't have enough data to actually utilize the power of AI. So actually, I think like IoT is going to explode. The second trend I've observed is that we are talking about almost like an emergence of IoT 2.0. It's almost like you don't look at the instrument giving you the result of a pregnancy test. It's the instrument that gives you all the inner working of the chemistry of that device. If you get that data out of the system, then you have IoT 2.0. You can imagine the volume of information coming out of that machine is a lot more. Meaning, let's say if you want a robot, you don't just get the end position, you get the inner working of the robot. So there are a few other notes that, you know, is all related to when you have IoT and when you get that data, all of a sudden normal distribution is irrelevant. You care about tails, you care about shapes, calibration, recalibration, all needs to go automatic. So it's a foundational step to get there. Number 3 is how do we get to explainable predictive maintenance? Because if you don't explain it, people don't trust it, they don't change their business processes. So you really need to establish, number 1, anomaly detection that is sitting on top of classic reliability analytics. People know reliability, and anomaly is just something that happens. You really need to have both. There are certain requirements that if you need to test your AI developer against them. If it happens a lot, it's not anomaly, it's just another regimen of the system working. Number 2 is if you don't have a system to reduce the false positive controllably, you will have a massive adoption issues. This is not going to go to production. Number 3 is you always need to have that feedback loop to get the inspection or the quality data into your training loop. If that doesn't exist, perhaps kind of like that's not a good place to operate. It's very challenging. And then the other thing to keep in mind is because anomaly detection is by definition it's rare, there's an economy about that data. It just doesn't happen a lot. To train your system, you need years and years of observation for the data to build up to be enough to give you something like you just actually saw in the last call that was about battery. So why we need an ecosystem, this is not a reason. As a consumer of this AI, you don't have everything. Context is everything. You need to collaborate with the builder of the system. It takes 2 to tango. So just pretty much like by having the operation running that system, you cannot create all the failure modes, all those root causes that you need to train your AI. These are scenarios you haven't seen before. So the key is to have a lab dedicated to generating the data. You cannot simulate that, except if you have a fresh principle physics of the system to generate those faults. You need to observe those anomalies. Pillar number 4 is we go to the explainability slash. They're not the same thing. We need to know the difference, etc. There's not enough time to get into it, but overall, this is an example of what we did. So these are 2 different root causes, and then red shows where the sort of heat is, like why we say it's root cause 1, why we say root cause 2. As you see, this is one of the examples. The experts cannot do it. This is like one little thing, happens, very quickly, milliseconds. And then it's basically coming from this example that I think a lot of you know, that the AI was assigned to pick between wolves and huskies, and it was doing a great job until later on it turned out it's looking at the background color. If it was green, it was a husky. So you don't want to fall victim to that scenario, because that's pretty much everywhere. Now, this is an example of something like that, basically this model implemented in real-time production of a system deployed. The other thing is, a lot of people are going to benefit from this AI system that you're going to get from the ecosystem, but there's a big timeline of it. So the moment the vehicle gets designed, it's probably like 5 years, 7 years before it actually goes to production. If you want to give the vehicle designer the benefit of having AI in his manufacturing, you need to talk with him now to have him in production a few years from now. So how to bootstrap this time, that's a whole different topic. But these are all the stakeholders that would benefit from every aspect of the way, from the footprint of bringing in AI in manufacturing. The other one is like, do not forget the public perception, especially in manufacturing. This is a real article from a real website by very real and serious people. They're just saying strategies to confront automation. So this is a reality we are dealing with in manufacturing. The same article, this is a major talking point. These are estimates of McKinsey. But the same article basically has a, coincidentally, a Las Vegas example that as long as you give a heads up to the workforce that, hey, you're working on this project and this might have impact on your job with a certain amount of time that they can retrain or repurpose or something, it's probably good. This is the same article. So this is a big portion of the car, because the person who's going to annotate the data, tell you how the business process works, is the same person who feels threatened. Like, you really need to keep that in mind. This is a sort of a, feel free to use this anywhere. This is the business use case for any AI and IoT project in manufacturing. So when you sell a system, the impact of it on a car is super small. If you want to charge the AI as a percentage of this number, you cannot sponsor it. You go bankrupt. It's not enough money. You need to point out to the overhead of managing thousands or hundreds of that system over the 10 years. And these are all the overhead. This is like, I use the welding example. You need somebody to keep going, recalibrating that adaptive thing, right? If you consider the salary, et cetera, it's 25 cents a car. You need troubleshooting for when that happens. There's training. There's maintenance costs when they go to maintenance shop. And there's the cost of inspection of a car at the end of its line. And then if they want to develop it in-house, there's whole IT costs, et cetera. So this is what we are shooting for. And you see it kind of like gives you that kind of number. So I'm pretty much appreciating anybody in auto who has more accurate numbers or like better examples. This will build up any business case for any project. And this is just ignoring the whole recall and the capital market impact of any issue, etc. Again, I'm very open to feedback on this one, but this is going to be the market cap value for any IoT and AI project. As you see, it's much bigger than the hardware side, but yet to be realized. This is an example of a tool that we did, example of a solution. Like, the workflow needs to be very clear. The bottom line is we do, based on the whole like Husky thing I showed you, we give users like a specific risk per joint of the car and what's going on with this. Overall, these are the major elements of any quality thing in any software. They do Pareto analytics, everybody does that. You need to forecast the faults in upcoming days or upcoming weeks. Upcoming hour is not short enough. They cannot act with that data. You need to have a system to adjust the programs, the adaptive thing we talked about, real-time monitoring, and a few more items. This is an example. We are forecasting next 2 weeks of any issue with the manufacturing per device, per etc. So this is a device-specific model. Every system has its own model. We are not using a statistical stuff here. So now the solution for all those sort of like fundamental problems is really to you build an ecosystem that goes beyond just sharing or like sending somebody data or just putting governance in place. As you see, this is, by the way, a big initiative in Europe called Gaia X that they have in place for all the car suppliers to share their data. You see there are different use cases are like interfacing, and there are many different chains. Every one of these nodes is a different company that is providing that material or providing that insights, and they all need to get integrated together. So to get streamlining the process of building such an ecosystem that they are trying to do, these are observations that it should not take 60 days or 90 days for you to vet a vendor. If you are in that environment, it's not going to work out well. You need to really sort of bootstrap that one. We can talk about it later. You need to have a sandbox environment because you cannot take them to production. You need to build that to test these different vendors. You need to check for capabilities to create the data that you need. And then you really need to have an expert-friendly environment for annotation. These are observations that how you get to this point is for your solution, and that's it. Any question? Thank you.
Any questions from the audience? Okay, well, thank you very much.
Oh, there was one question here. There's one question.
Sorry, I missed you.
So getting access to the data is obviously difficult with different customers, vendors, multiple stakeholders. So how did you go about with data acquisition and making it anonymous so that you could actually use it for aggregate data in comparison and looking at it with modeling and stuff like that?
There are vendors who do that, right? But it's beyond that, right? You need to have legal support. You need to have sort of like organizational readiness to even share the data. The problem is people want to have a business case to even put hours to share the data. And before looking at the data, you don't even have a business case. So it's like a catch-22 thing. So this is the whole thing. Like all these elements that I mentioned is like the way to check for a vendor and how to build the ecosystem. But then the whole meaning of ecosystem is that a place that you can just put the data and other people can just come work with it. It is not like you actually like give it one-to-one. That's ecosystem, right? But yeah, these are the things. Yeah, have this 4 or 5 requirements in place, and then these are some elements of solution. Yeah, the big players, let's say big OEMs, they need to have sandbox. Actually, I'm never aware of any, but we have some. And it helps us a lot in the last few years to go through a lot of startups really quick, really fast, and even know how their performance stands up, because their performance based on some benchmark doesn't translate into your problem. And then also the stream, like if you spend 60 days to bring one vendor in, there's a good chance that you're not going to try the second one. You don't want to spend all that time. So this is another organizational thing that needs to get solved. Basically, these are the foundation of building something that kind of like enables that ecosystem. Yeah. Then that's all, I guess. This is a big topic. If you want to have a discussion later about it, I'll be more than happy. There's a lot of lesson learned, yeah.